Hey everyone, Mr. Chung here. We are moving on to chapter 22, which is a bit of a change of pace, but hopefully one that a lot of you will enjoy. And I found online that there are PowerPoints that were already made for a lot of these chapters. So wish I had found this earlier, but it was good for me to make PowerPoints for you guys as well. But let's get to it. I edited this PowerPoint a little bit, but it comes from the textbook itself, so it follows along with the textbook. So if you have been reading along with the textbook and taking notes, as you should have been, it should help you. All right, so chapter 22 is all about organic chemistry, and we're going to get into what that means. But let's start with the question, why are some fossil fuels gases, some liquids, and some solids? That is kind of like one of the big questions that this chapter answers. Now, we all know that the gas used to fuel motorcycles is a liquid, but it contains mixtures of compounds that are called hydrocarbons. And so chapter 22.1 is all about hydrocarbons. So we're going to do the first half of that today here in class. Now, in your book, key question, first key question is, why does a carbon atom form four covalent bonds? Now, this is review, so hopefully most of you know this already, but let's go over that really quickly. Before we get there, just to comment on why this is called organic chemistry. Like 200 years ago or so, it was thought that only living organisms could synthesize the carbon compounds found in their cells. Now, that has since been shown to be not the case, but that's what was believed 200 years ago, and as we've seen at other times, what people believe when things get named kind of gets the names to stick. All right, so they call these compounds organic compounds, organic meaning life, living things, and the study of these compounds was known as organic chemistry. And so what has happened is today, organic chemistry includes the chemistry of almost all carbon compounds, even if they are not formed from living organisms. Now, we are going to talk about hydrocarbons. So the simplest organic compounds are called hydrocarbons. And hydrocarbons, pretty straightforward. It's an organic compound that only contains carbon and hydrogen. And so there are a lot of rules that dictate these hydrocarbon compounds. And we're going to go over the simplest ones today, the simplest types. Now, the simplest of the simple are methane and ethane. Methane, CH4, is the major component of natural gas, so you should all be familiar with that one. And ethane is C2H6, not pictured here. Now, to go back to that question, why do carbon atoms form four covalent bonds? Okay, remember, a carbon atom has four valence electrons and a hydrogen atom has one valence electron. So one carbon atom can form a single covalent bond with four hydrogen atoms because they're going to each share, and that will make them happy, because if you look here, the carbon has 8 valence electrons around it, and each hydrogen has 2. Hydrogen is special. It only wants 2 valence electrons, but everyone else wants 8. So carbon's going to form 4 bonds. Now, it doesn't have to be with hydrogen, but because we're talking about hydrocarbons today, we are talking about hydrogens in this particular instance. Now, so the key answer to the key question is just because carbon has 4 valence electrons, a carbon atom always forms 4 covalent bonds. Now, remember, that can include double or triple bonds, but still, it's 4 bonds total. Okay, so methane is a little bit weird because there is no carbon-carbon bonds, but the majority of hydrocarbons have carbon-carbon bonds, meaning there are carbons that are bonded to each other, and then there are also hydrogens bonded to the carbons. Now, the ability of carbon to form stable carbon-carbon bonds is one of the reasons that carbon can form so many different compounds. We will get to it eventually, but like we're talking about hydrocarbons now, but fat has carbons in it, proteins have carbons in them, your DNA have carbons in them. So carbon forms so many different stable compounds. That's why your entire body is made up, and this is why it's called organic chemistry, because most of the carbon compounds have to do with stuff that has to do with your life and your actual living, like your day-to-day breathing, et cetera, et cetera. So this ability of carbon to form these stable carbon-carbon bonds is one reason that carbon can form so many different compounds, and one reason why those carbons are so important for us, because they're stable. That really helps as well. Now, representing hydrocarbons, this is where, if we were in class, it would be great to have ball and stick models, but you're just watching this online right now. But as you can see, the structural formula you should be familiar with, because that's what we did back in chapter 7 or so. And then the ball and stick model is what we would do with 3D models if we had them. And then the space filling model is a more abstract representation of what's going on with hydrocarbons. And so that's kind of like a more realistic view of what things look like, except for you don't have these bubble things in your body. Those bubbles are clouds of the probabilities of where the atoms can be. You don't need to worry about that. But anyway, those are three of the models that we have. And we're going to get into this a little bit more later. All right, so we're going to talk about alkanes today. Okay, so what are two possible arrangements of... Actually, I'm not going to get to this. Okay. What are two possible arrangements of carbon atoms in an alkane? Okay, alkane, this is important. Okay, when you see alkane, or this suffix ane, A-N-E, that means you have a hydrocarbon in which there are only single covalent bonds. Okay, no double bonds at all. Now, the carbon atoms in an alkane can be arranged in a straight chain or in a chain that has branches. And we're only going to be talking about the straight chain alkanes today. So we're not even going to talk about what branched chains look like for today. Now, ethane is the simplest straight chain alkane, that just means an atom that contains, an alkane is just contains carbon atoms one after another in a chain, and then hydrogens filling in the rest. So propane has 3 carbons, butane has 4 carbons. Now here we get to something that you're going to have to memorize. Okay, but before we get to that, introducing a new vocabulary term, the straight chain alkanes are an example of what's called a homologous series. And that just means that as you add carbons, like here it says, if there's a constant increment of change in molecular structure from one compound in the series to the next. Okay, all that means is, like, as you add carbons, the thing that you're adding to your formula overall is always going to be the same. It's like using the same building blocks, and as you're building things out, you just keep seeing the same thing over and over again. Now, for alkanes, every time you add a new carbon, you're just adding a new CH2 group. And it'll be easier to see that if we see the pictures. So let's take a look. Ethane is CH3CH3. Okay, if you go back to this picture here, okay, see ethane here, C, there's 2 C's, and then because each carbon, remember we said forms 4 bonds total, so each carbon has 1 bond to the other carbon and then 3 bonds to different hydrogens. So ethane is C2H6, but if you look, the reason why they're saying CH3CH3 is because this carbon has 3 H's on it, so they call that CH3, and this carbon has 3 H's on it, so that's CH3. So that's how they get CH3CH3 for ethane. Now, if we go back here, okay, so ethane is CH3CH3, okay, but to add a carbon overall, we're going to add a CH2 in the middle, and that will give us propane, C3H8. Okay, so we get C3CH2CH3. Okay, but then propane, if we want to go one more carbon above that, then we add another CH2, and then we get butane, CH3CH2CH2CH3. Okay, and the overall formula are pictured here. Ethane is C2H6, propane is C3H8, and butane is C4H10. Now, you might be asking yourself, wait, why are we adding CH2s in the middle and not CH3s in the middle? And here's where I will let you think about that a little bit. Just think about, why are we adding CH2s in the middle, not CH3s? Okay, if we go back here, if you look at C2H6 here, if you imagine you put a carbon in the middle, that carbon is going to have 2 bonds, one to the carbon on the left and one to the carbon on the right. So it only has 2 bonds left for extra H's, which is why you add the CH2. Okay, so that's why every time you add an extra carbon to an alkane, you're only adding a CH2. If you're having trouble processing that right now, write out, I encourage you to draw out the structural formulas of propane C3H8 and butane C4H10, and it'll be much easier to see. And you're going to be practicing that later anyway. All right, so like I said, every alkane has a name that ends with the suffix -ane. These are, if you were in organic chemistry and it wasn't the end of the year, you would have to memorize these. It just goes like, the first four are weird. Methane is 1 carbon. Ethane is 2 carbons, C2H6. Propane is, this is written wrong, but I can't fix it because it's not, oh, I can fix it. Never mind. Propane is 3C3H8. Butane is C4H10. So look, every time we're adding 1 carbon, methane is 1, ethane is 2, propane is 3, butane is 4. Those 4 are weird. After that, it gets easy, quote unquote, because it's the same prefixes that we used for naming formulas before. Pentane, 5 carbons, hexane, 6, heptane, 7, octane, 8, nonane, 9, decane, 10. Okay. I'm not going to make you memorize these, but you would if you were taking organic chemistry. And they're pretty straightforward, honestly. Okay. So if you're trying to draw one of these, all you got to do is write in all your carbons, bond them to each other, and then just fill in H's everywhere else until you have 4 bonds on each carbon. Okay, so it's pretty straightforward. So here's C4H10, butane. You can imagine you just write C, 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 bond them all, and then put in H's to fill in the rest so that each one has 4 bonds. Look at it closely. You'll see each carbon has 4 bonds done, and they're all single bonds. Now, what that was the complete structural formula, but you'll also see a condensed structural formula. Basically, these hydrocarbons get really long, and chemists are really lazy, so we want to make them see written in a shorter way. And so we do a lot of things just understanding that they're there, and that's what we're going to practice today. So a condensed structural formula, okay, just says, okay, CH3, CH2, CH3, okay, with an N here, and the N is just how many CH2s are in the middle. Remember, it's the same pattern every time, so we're just going to put it in there, okay? And so the way you can write it is, for butane, CH3, and then 2 CH2s in the middle, and then CH3. Okay, so that's one way to just write it shorter. Now, there are several ways to draw condensed structural formulas, and here are some of the ways, and this is what you're going to be practicing today. So, butane is C4H10. The complete structural formula has 4 C's with 10 H's around it. Now, a condensed structural formula with CH bonds understood, just write CH3, CH2, CH2, CH3. And again, it's just like this is a CH3, and then a CH2, a CH2, and then a CH3. Okay? But then we get even lazier. We don't even draw the bonds between the carbons. Okay? We just write CH3, CH2, CH2, CH3. And then we get even lazier. Okay? We don't even write all the CH2s in the middle. We just put a parenthesis around it and say that there's 2 of them. And then we get even lazier and just draw the carbon skeleton with all the hydrogens and the CH bonds understood. Because remember, every carbon's always making 4 bonds. So if you know I have these 4 carbons here and they all have single bonds, I know I can count how many, I can figure out how many H's, okay, are around each one. And then finally, we use what's called the line angle formula. We don't even write the C's out. Each vertex here, okay, is considered a carbon. That one's pretty complicated, or abstract, so we'll leave that one as extra credit. Okay, so we're going to stop here, and I'm going to go over what you're going to try to work on. I'm going to make this bigger. Okay, so what you're going to do is I gave you 4 different alkanes, and you are going to write these different formulas for each of them. Okay, but use butane as an example. Okay, so ethane, I will tell you, is C2H6. The other 3 you can look up on that chart that I just gave you. Now, a formula for an alkane is always CX and then H2X plus 2, so you should be able to figure it out. But what you're going to do is you're going to just draw, like you can draw this yourself if you want, but you know, this is how I did it. That line is a pipe. It is the backslash. You hit shift backslash, you can get that. Okay, but if I'm going to write C2H6, you know, I'm going to make the structural formula and I can make it look like this. Okay, so then I have C2H6 here, right? And then I just go ahead and then using this C4H10 as an example, go ahead and fill in the rest of that. Okay, so that's what you're going to be doing. Okay, you know what? I'll do ethane with you guys right now, and then I'll delete it before I give it to you. Okay, so ethane C2H6. Now I see that that's just CH3, CH3. Okay, and I can put a bond in the middle in this version. Okay, well, you see how I got that, right? CH3 and then a bond to another CH3. So that's this row. Okay, condensed structural formula with the CH bonds understood, right? I've drawn the CH bonds. I've included the CH bonds by just saying CH3. And then here, condensed structural formula with no CC bonds. So I just write CH3, CH3. Okay, carbon skeletons. I don't write any of the hydrogens in. It would just be like that, CC. And then the line angle formula, what I'm using for this is actually the slashes. Like I said, this would be extra credit. I made like the font size like huge, like 48, but then I can just put a slash in here, and that is kind of like the line that you're drawing. Like if you go back to this, like this line that they're drawing here, I couldn't figure out how to actually draw it, so I just use these backslashes. If you look at this one, it's C4H10, you see 1, 2, 3, 4 vertices. All right, and so this one has 2. Don't worry about the line angle formula if you have trouble doing that. Anyway, that is going to be your work for today, so you can go ahead and do that. If you have any questions, let me know. Other than that, stay tuned. We're going to keep doing these hydrocarbons going forward.